message. Anyway, so this is how it works. And so with penultimate hop hopping, what will happen is it says implicit null to it. That is the signal. It's signaling that you can remove the top level because I don't need it. And then the same thing will go. And as you can see, I don't have any out level because I said implicit null. Previously, I was saying 100 and it was putting 100 here. This time I said implicit null. It does not have now any out level. So when the real packet comes, the rest of this is control plane. So the information spread among the routers. So when the real packet comes, the packet formation is same at the ingress router, but when it comes to this router, it has the table, LFIB table, incoming with, let's say, 200, but there is no outcoming one, implicit null. So what we'll basically do is to pop the top level. It will keep the next level and payload, because next level is the meaningful and very important for P2 to identify which BRF or which VPN it's gonna pass the packet through. Okay. And now you can say that this router will basically do two things. One is the MPLS packet processing, looking at the LFIB table, and once it finds out that this is the VPN I'm looking for, it will then look at the routing table to identify which exit interface this or the VRF, which VRF I need to pass this packet. So there's two lookup that will be done by PE2. And then the level will be removed because this guy does not understand MPLS. Okay, so very short. I know there can be many other topics about LDP itself, but in short, LDP is a new protocol that is needed to distribute levels, and LDP cannot do traffic engineering. So LDP is best effort. Okay, so LDP can only do best effort. If you want to do traffic engineering, it cannot give you that. So for traffic engineering, we need a new protocol called RSVP-TE, or Resource Reservation Protocol Traffic Engineering. So with MPLS, at least two additional routing protocols comes into the picture and is a requirement if you want to do traffic engineering as well. So this has been a challenge at the beginning because the RSVP-T is not really a very efficient protocol, but for MPLS, there was no other option. So RSVP-T, what are the drawbacks? I don't have those slides here, but you can read. RSVP-T is very much connection oriented, and it's like it keeps the connection up by sending these synchronization messages. So it always send, hey, I want to maintain the connection. So it's always keep on saying that, and then also it has to do in every single router. You do the adjacency and things like that, and then you have to do several other messaging to reserve. So it's called resource reservation protocol. So you basically reserve the bandwidth for this path. So when you talk about LSP or path, traffic engineering means I want to select the path, how it will go. Now I'll tell each of the link that reserve 500 meg for this path. I need that. That's a resource reservation protocol, and this is a difficult way of managing the traffic engineering path because it's not very efficient. But for MPLS, no other option. It was the only protocol that can be used. But for segment routing, why segment routing came? Because of this challenge of MPLS. So for segment routing, we now need to know some new concept because I wanted the MPLS concept. Otherwise, this will be a little bit difficult. That's why now totally focusing on SR segment routing, and then I'll focus on SRv6. So at the moment, SR or segment routing will be on top of MPLS. Okay, but overcoming those problems that we had. So what was the problem? We had the LDP requirement, another routing protocol needs to be run. We have to run the RSVP for traffic engineering if you want to do. So these are the challenges. Now, segment routing is basically kind of a source routing. I want to tell how the packet will move from the source. So it's like steering the packet from the source with some sort of instruction, and that's called segment. The instruction is the segment. And with some policy, if I want to do traffic engineering, that's the policy will come. So these segments or the instructions can be represented as a topological, or which node I want to use or which link I want to use. Links are adjacencies and nodes are the router that I want to go. So basically from the source, I will say go to the destination using that intermediary router and that link between these two routers. So make sure how you want to go, I don't know, but make sure you touch those instructions. And these instructions are the segments or the elements, you can say, right? Now the segments can also be services. I can say, go to that destination and use that DRL. So that's basically what we are doing with BGP. Okay, this is like service and applications. Now, several different terminologies. You will see that local segment and global segment. So we'll talk about this more of all these terminologies. And how it works is the source determine the path, and I can tell that going to the destination you touch this node, but I'm not telling you how you go to the node. So go to the node based on your best path. I don't care, but you have to go to that node before going to the destination. So, and if it's an adjacency, it's like a link between, let's say, two routers. I'm saying that use that link because I want you to go through that link. So that these are the segment instructions, and these can be shared, or this in each of the segment will have some ID. This can be a level. At the moment, because I'm talking about MPLS, SR or SRMPLS, that means I'm going to use level as my ID of node, as my ID of adjacencies. Okay. Now, the intermediary routers, usually they will just check the segment list and will do like a normal packet switching. If it is MPLS, it will do that level switching, normal switching. But no state is kept. It means that for MPLS, the other MPLS that we have just seen, it needs you to keep the states. Like for the path, it needs to keep the information of the path with RSVP, TE, and with LDP. But here, the intermediary hops basically just do switching based on its ILM, and really not need to remember or not need to process like an RSVP, TE. They need to maintain each of the states for a certain path. So there are two data planes that can support this segment, because segment routing, the control plane will be taken care of by the routing protocol. We'll come to that. But how about the data? Data moves. Previously, we saw in MPLS that data plane uses level to pass the packet, and the table that is used is LFIB. Okay, but here segment routing, that means steering packet from the source will decide how the packet will move, can be done by either MPLS as the data plane or IPv6 as the data plane. When we use MPLS as the data plane, we call it SRMPLS, or segment routing with MPLS data plane. When we use IPv6 as the data plane, we call SRv6, or segment routing with IPv6 data plane. So when I'm talking about SRMPLS, means the packet will move with the levels, like the level we have seen. When I'm talking about SRv6, the packet will move with IPv6 address as the level, not really a random number. The address structure is 128 bits. So it quite fits with the IPv6 address structure. That's why it's called SRv6. And it solves several other problems as well. And we'll see very soon how it can be done. So first, some definition. So segment, I said some instructions. So the source will say, go to the destination using this path. So this is a segment. You can say, level or something, level stack or something like this. So this is the segment. Segment ID is either MPLS level or the IPv6 level that I told you, like IPv6 can also be used. So segment ID or SID is basically, you can use a router with a level, and you can identify that router using that level. Or you can use the router's IPv6 address and you can identify that level, that router. So that's called node SID. So I'm identifying a node using a segment ID. The ID can be a MPLS level. The ID can be a IPv6 address. Okay, so that's called SID. Global segment. Global segment is unique to the whole domain, and it has to be known to other neighbors. But the local segments, for example, we are doing a VPN example. PE2 knows the meaning of the VPN level, nobody else knows. Something like this. So it's a local concept. So that's called local level. So assigned by the router locally, but didn't mention to anybody else unless they need it. So these are local MPLS, local SL levels, and there are some global SL level. What is the block? Block is the range of level that I want to use. I'll reserve it, but I'm not using it at the moment. So it's a block from where I will assign the levels. It can be an IPv6 subnet from where I will assign the level. So that will be my block or segment routing global block. If it is global block, means everybody will get the information. For example, if I announce a /32, that's a big block I reserved. I can create so many addresses, and each of the address can indicate an application, a service, could be a VRF, could be the router itself, things like that. So node adjacencies, services can be assigned individual IP addresses from that subnet. So that's like a block, and then individual segment ID can be generated from that block. So block is a big range, and individual segment IDs can be generated from that block. For the other neighbors, if they know the block, that's called global, means they knows it. If they comes to me and I have a local table where I put different types of levels out of that big block, and they don't know what it means, that's my local segment or local segment block. Okay, so you basically announcing the block which is global when it comes to you, and you know that which service it's looking for because you have a local table as well. So local information does not need to go to the other routers. Segment routing policy. You will see that it is quite common when we are going to do the traffic engineering. Policy is what I want to do. Basically, the instructions of this routing. So I'm saying, you go to the destination, you go there, and finally reach. So that's the instruction, and it's a policy or segment routing policy. Now this happens in the control plane, and that's why you see something called PCEP or Path Computing Element Computation Protocol, or PCP. Sometimes you can say like this is like a arrangement, because the question comes after this is, who is going to tell the source router to create the policy, and who is going to impose the path? Because the router doesn't see the whole path. The router only sees its own path because it has a routing table. Based on that, it just decides. If there is a controller who knows the path and who knows everybody's information, that controller will have visibility that, hey, if you use that path, it's better. And if that path has a node is down, you use the other path. So the controller is the brain, and it can see that. That is done by a protocol called PCEP. And that's, I'm not going to cover today because that's then again going to be very big. So you can say it's SDN. In simple terms, you can say it's SDN, or software defined network. That means the controller needs to have peering relationship with the routers, and the router will inform its topology information to the controller. And then it has another requirement how the router will know, because BGP is a protocol that the controller can have a peering with each of the routers. The controller can be a BGP speaking router and collect the BGP routes. But how about OSPF metrics? The internal routes are through OSPF, not through BGP. And the interface bandwidth and things like that, and that's called link state information. So that's why BGP has a new TLV that has the capability to carry link state information, and that's called BGP LS, BGP link state. The weakness of link state routing protocol is you have to physically connect to your neighbor. When you run OSPF, you cannot talk to a neighbor which is very far from your link. You can only do neighborship with your next connected router. That router's responsibility is to collect the information and give it to you, not really you are talking directly to other routers. But for BGP, it's easy. You can do multi-hop BGP. In IBGP or eBGP, you can do peering with somebody because it works on top of TCP. And TCP means if you can reach to somebody, you can talk to them. That's TCP. But OSPF does not work on TCP, or ISIS does not work on TCP. So remote peering is not possible. That means if controller wants to know OSPF metric, it needs to be directly connected to every single router in one OSPF domain or the ISIS domain. It has to have peering with everybody. So controller-based solution is very difficult to implement with link state routing protocols, or in short, currently the only option we have is actually link state routing protocols. The RIP and EIGRP, all of them are dead, right? Nobody uses that anymore. So the link state routing protocol has this vision, and controller-based SDN solution is not possible. Instead, if BGP can be implemented, it's possible because BGP, you don't need to talk to all of the BGP routers to get routing table. You just need one BGP neighbor in one certain AS to get their routes. That's it. So controller can do a BGP peering with one of their routers. And if BGP has the ability to get the intermediate, sorry, not intermediate, but link state information, like the metric, to go to that loopback address or that interface IP, because OSPF knows that, or ISIS knows that. If OSPF and ISIS can give those information to BGP, and BGP can carry them to the controller, the controller doesn't need to do direct adjacency with anybody anymore. So that's called BGP-LS, and is done by the TLV. How protocols functionality is improved based on TLV. Any protocol that is structured or architected is generated with the TLV can expand its functionality just by adding more TLV, more TLV, and more TLV. And ISIS has this, BGP has this, OSPF didn't have it in version 2, OSPF v3 has it. That means without changing the protocol or building a new protocol, you're just adding new functionality. So BGP-LS is a new functionality in BGP that can carry link state information, and that's what is used for the SDN and controller-based. What is SR domain? Like MPLS domain, the MPLS is speaking routers forms kind of domain. Segment routing aware routers are the SR domain. Active segment, the active segment is the instruction. Go there is the segment, for example. If I have 3 instructions there, first you go there, then you go there, then you go there. The first one or the top one is my active segment. When I complete that, I finish that part and I look at the next instruction. that become my active segment, and up to I finish that task, it's completely active segment for that segment. And then once I reach there, I look at the next instruction, that becomes my active segment. Segment list depth, like I said, if multiple segments are there, how many segments or instructions I have? Let's say I have 3 instructions, the depth is 3. Okay. Now the definition changed a little bit, even though it's not necessary. It's not necessary to remember, but it's changed a little bit. So push is still the same name. Next is the pop. So you remove a level, that becomes next. But if you swap, it becomes continue. Okay, and we'll see how it works. It's simple in the when we do the animated like diagrams, it's gonna be easier. Now I'm going to the SRv6 or IPv6 data plane for segment routing. And this part is important and mainly my main topic, and I might not be able to finish it before the break, but we'll stop where we can, and then after the break we'll continue, and then we'll do the lab. Because the lab can be done any time you want, and it has its own explanation and instruction. There is no need of somebody to explain it because the lab is nicely done. We'll see. Now, data plane, I'm saying that the IPv6, the packet header itself will have the ability to carry instructions, and we'll talk about it very soon. So we need a new routing header type to carry the segment routing information, and then also the segment routing ID or the segment ID in this case is not the MPLS level but IPv6 address. That means its structure is its size is 128 bit. There is a destination address, how it calculates, and there is a concept called segment routing header, how it's done. I'm going to show you in a diagram here. So first of all, IPv6 has a additional field called next header. IPv6 next header means instead of the payload, read more header. I'm instructing the router that after this header, payload should start, but don't think payload is coming because I say another header will be here. So it's an extension header or next header. So I have a new routing header called 43. The new extension header called 43, which means routing header. Okay. Now routing header means I will have a different header format because I wanted to tell the router that this is not payload, it's another header. Read the header first. So this is the format of the header. The header, any header has a next header in IPv6. So next header is basically after this, there will be something else. It can be payload. Payload means either TCP or UDP. So next header indicates that value, or the next header can be different header. But I need this segment left and routing type information. So this explanation more easy to understand here. Look at this part, okay? This is a normal IPv6 packet header, normal packet header. If you don't have this part, next header will be either 17 or 6. Right? I mean TCP or UDP. That means the payload will start after that. So this part will not be there. Okay? But because I want SRv6, I'm going to utilize a predefined header, which is called routing header, and its number is 43. So when the router look at the IPv6 header, and this is the IPv6 header, when it look at the next header, it looks for 17 or 6. But there's no 17 or 6. That means it is expecting some header, not the payload yet. So in the new header, which is the next header, which is 43, I have a routing type called 4. So routing header type 4 is segment routing v6 or SRv6. So here I have a couple of things. Like I said, next header will be, here it will be 17 because this is the payload, or 6 if it is UDP packet, right? So here, segment left, these are the list of segment. I told you that I can give you multiple instructions, go there first, then there, then there. So every single instruction is a segment. and this is a list of segment where the top segment is the first instruction and the bottom segment is the last instruction it will execute, and each of the instruction is basically IPv6 address. Up to this point, it's because this is important slide. This is something that we need. So segment left is, for example, if I have 5, so I'll have segment 0 to 4. If I'm on the number 2, that means I have 2 left. So segment left will be 2. Okay. Every single instruction once done, the segment left will be reduced by 1. Okay. Yeah, last entry will be this. This one is the last entry, so it's an indication of that this is the last. So this entry, the last entry, will be understood by the last router, with the last this is basically the destination. You can understand, oh, I'm the destination, so I don't need to do segment routing anymore. I can remove the header and I can make it a real IPv6 packet and pass it to the next router.
So the total number for segment routing is 43. The total number.
The extension header number, yes. 43 is the extension header number.
Oh, extension.
I mean, it's not even segment routing header. It's called routing header. Routing header can be different types. Segment routing SRv6 is type 4. So if router finds something else here, it's not SRv6. It could be something else. So these are defined numbers to indicate the router what it's gonna look at or what is the meaning of it. So if, for example, if this is not 43, if, let's say you want fragmentation, you probably have some other numbers. You want ICMP, you have other numbers. When you have 43, it's already defined that next header is the segment routing header. So it's called SRh, or segment routing header. So this part is SRh because it is indicated by 43. And SRh type has to be 4. Yeah, so these are some information that router will, because router reads header and then understand what to do. Yeah. So this is basically, this part is expanded like this. So you see that I have so many lists of instructions and each of them are marked with the IPv6 address, and it can be many, and then final is this one. So next header, basically after this segment routing header, what I'm going to do is the next header. I'm not going to point much about it. Let's look at the segment left. So segment list is the instruction already covered here, starting with 0 and end at a number, and that last number is basically the last entry. Segment left is very important because which instruction is at the moment we are processing. Maybe we are processing 0, then segment left is number n. So if I have 5 instructions, if I'm processing 0, actually I have this number will be 4, right? If there are 5 instructions, it starts with 0. This is 4, so 4 will be here. If I'm on the second instruction, 3 will be here because the instruction left is 1 less than because I already processed 1. So this is the explanation of each of them, and this will be understood here. So let's say I have a SRv6 packet. We'll talk about how come we build this packet later. But at the moment, what happens is SRv6 packet looks like this. In many cases, this part may not exist in SRv6. In SRv6, it's not mandatory to have a segment routing header. In some cases, we may not need that. I'll come to that part soon. So let's say I have IPv6 header, segment routing header, and then I have payload. Now here, when I'm talking about IPv6 header, and let's see a diagram. R1 is an IPv6 address, R3 is an IPv6 address, even though we mentioned R1, R2, but basically these are addresses. To make it simple, we made R1 and R3. Now, actually, the payload itself has its own address because this was originally coming from an IP device, IP-enabled device. The whole thing put in the payload, so they might have some IPv4 address. So the payload can have IPv4 packet inside. Okay, you got the point? It can have IPv4 or L2 as well. So anything can be in the payload. This one is how it is formed is it will look at the segment routing header. The first of the list is R3, so the destination is R3. So the IPv6 packet which is created will have a source IP of the router who is sending the packet. The destination IP is not the ultimate destination yet. First destination is R3. So my target is to reach to the first segment, the end of the first segment. Okay. So this packet in normal IPv6, we know that source cannot be changed, destination cannot be changed. It will be same on all the OA. Doesn't matter how many routers moving. The source IP and destination will not change. But here it's different. The source IP will not change, but destination will keep on changing as long as I'm not reaching at the last segment of the instructions or segment list. So when the first packet created, source is my destination is in my list. I see R3, so that's my first destination. Once I reach R3, it's up to R3 how it will recreate the packet, and we'll come to that how it recreates the packet. So at the moment, this is the active list, and an active list is this one, and destination is R3, and segment left is 1 because there are 2 instructions. I'm dealing with 1, so this is 0 and this is 1. Remember, the list starts with 0, so 1 means the last one, so left 1 because I'm currently active. This one is active and I'm left with 1 instructions. So if I now see how this moves, so let's say R1 got a payload like a normal packet. It can be IPv4 packet, it can be IPv6 packet, it can be any different, even legacy packet, legacy protocols, doesn't matter. It can be L2 frames, so it will just be in the payload. R1, so this whole part is my SR domain. Okay, the whole part means all of them understand segment routing, and this is the PE or the provider edge. So its job is to add or push the levels. Here we'll not talk about level, we'll talk about the segments that's gonna push. So this is the SR source node. Source node's job is to look at the payload and look at the destination. And basically, because it's quite similar to source routing, so R1 will decide which node I'm gonna go. Now here comes the SDN. If I had a controller, the controller will tell R1, you have to go via R3 and then go via R5 in order to take the path that the network admin wanted. But here, just to visualize, let's say R1 has been instructed by the network admin to touch R3 and then to go R5. So because this instruction came already, so R1 will make a IPv6 packet with a segment routing header, and the header will have a list, and for R1, the active is R3, which will be the destination address, and left with 1 segment list. Okay, now it's targeted to reach R3, not to the ultimate destination. How I go R3 again comes with the best effort. So I'll choose the best path to go to R3. Okay, I'm not choosing the best path to go to the ultimate destination, but to the first my active list, active segment I want to find out. So let's say via R2 is my best path to R3. R2 now become a transit node, and for transit node, it does not need to look at the headers, the segment routing headers. It will just look at this header and will basically work as an IPv6 packet, normal IPv6 packet. It does not even know that I'm dealing with the SRv6 packet, because it does not read this. It's just look at this. My source is R1, my destination is R3. So I'm going to take my routing table and look at the routing and just go to the path. So finally it comes here. R3 look at the header and it's the destination. And destination, and it sees there are 1 more instruction left. So it will just change the R3 with R5. Tell next neighbor, I don't know how you take me there, but take me to R5. So when the active segments become R5, I don't have any other segment left, so it will become 0. So this is like the endpoint for the active segment, not the ultimate endpoint. Every segment has its last node as endpoint. So this is the endpoint, but not ultimate endpoint. That how it understand I'm not the ultimate endpoint, because it can see that there is a one segment left. So it will basically do is it will change not the source IP but the destination IP from where? From the list. The last, this one will be copied here. So it's basically copied this one here, and segment left reduced by 1. So it becomes now 0. Again, this one becomes a transit segment router. This one becomes a endpoint. But in our scenario, this is also called the ultimate endpoint because there is no segment left. So that's the ultimate endpoint. The transit behavior is same. It does not change anything. It just finds the best path to reach the destination. It will open it. It will see this is I'm the last. I'm the destination, and there is no segment left. This means that all the task has been successfully done, and so I don't need anything else. It will basically remove this and open up the payload if you want it. That look at the payload and then find your routing table. If it is an IPv4 packet, you have to say, look at IPv4 routing table. If it is an IPv6 packet, look at IPv6 routing packet table. If it is a VPN packet, look at the VRF table where it belongs, things like that. You have to instruct, and this is called local instructions. Remember I told you there's a global seed and there's local seed. Local seed does not need to be informed to other routers. So it just need to come here, and there are some local seed that it knows how to deal with it. And the configuration has to be done by the admin. If you want to just reach to this router, that means it has to process differently. If you want to pass the packet to somebody here, it needs to process differently. If it is IPv4, it needs to process differently. So every single instruction is now identified by IPv6 address, not by the level in MPLS. Okay, and we'll see after the break. We'll see how it works. So this is basically how we did. So finally, it will remove it and treat it as a normal payload. Reduced header, and that will be the last slide before the break. Oh, I took actually longer than. So reduced header, very quickly, and just this slide. What is the reduced header? You know, I know that the segment list, I'm dealing with R3. I don't really need to mention R3 in the list because I'm already dealing with that. So because the more level in the stack, it's taking the space from the header, meaning the payload becoming smaller. So I can actually remove the previously done tasks. No need to copy them. I just only keep the remaining tasks because remaining tasks will be implemented. So R3 not yet task. R3 will work here. So I cannot. R5 will be start working from here. So I don't need to remove this, but I can remove the previous task. That is the reduced header, the reduced segment routing header. So it will basically save some space from the header. That is the whole idea. Okay, let's take a break. Sorry for taking didn't realize. Sorry for taking another 10 minutes, but let's come back after 30 minutes, which can be 10:50, 10:45, 10:45, and then we'll start from there. Okay.
Okay.
Yeah. Thank you so much. By the way, do you have any question before going? We can have discussion if we want during the break.
Sure.
is something like this. CSR is a lot small. So I don't know why more. Is it running? Is it running?
Yeah, it's running.
Okay.
But I think the video recorder is broken. That because it should be controlled by this controller.
Oh, it's not working.
Yeah.
Okay. But where do you see this is running? Like, you go to home screen, return to meeting. This is the thing.
Oh, no. It just cause I scroll the meeting to there. This is
Okay.
a two screen.
Oh, this is extended.
Yeah, it is standard.
Okay.
And in the APAN60, the cheapest cost is lower than average. Yes.
The cost means the metric you mean? You know,
No, it's the first thing.
So because this is not a routing, does not have a cost. It relies on other routing. They have. So if MPLS has level by OSPF, then the cost that OSPF metric has will be the cost. If MPLS level can BGP, then the BGP's cost is the MPLS level. So MPLS is not a protocol itself. It is kind of a service. And it relies on the routing protocols metric to go somewhere. So MPLS is in short, MPLS does not have its own cost. It depends on which protocol is using to calculate it.
That's my. Thank you very much.
So 10:45, right? 10:45 AM.
Yep.
So second.
About 7 minutes. Also start.
I want to this not for video. Space. Yeah. You see that the number.
People.
Yeah, because they are saying because they are same like for the engineering movements.
Yes.
We have office they so this workshop is a kind of you can answer and bring it to show yeah. Very good. Yeah, I think they will if you come to a big point, you know so just it happens similarly like yeah. So we are all taking all these people you can force such as this one people close to the work. Yes, everybody knows that we want to be close. On top of something. So this almost. People in February. And the number is second of September. This month is similar also. Yes, there is a similar program first for this time we
Start in the plant. So, then she don't know, we can have it.
Yeah. Okay, is the audio?
Yes.
So going to start the next part. And this part is more of the segment routing, the IPv6 data plane.
We can use. Okay. Oh.
So the programming or programmability part is to program how the source will decide how to go to the destination and which segment will be added to the segment list and things like that. And then we'll see some of the functions and the behaviors. So let's see some of the functions and the behaviors. The functions and the behaviors are basically encoded like the IPv6 address. So the router will know that, oh, this address means that. Actions are encoded in instructions which can be identified by the address. So this is the seed or segment ID format. Previously we saw that seed is like MPLS level. This time we are gonna see the seed as like a IPv6 address. So the format is, of course, the whole seed length is 128 bits, but it is divided into several pieces to identify some of the aspects, like it could be a device, it could be a link, it could be a task. So let's see how it does. So the first couple of bits are called locator, and it's a variable bit, so you don't have like a fixed number there. Then some bits are called function and some bits are called arguments. But altogether, this has to be 128 bit because it looks like IPv6 address. Segment routing data plane is IPv6 and the seed looks like address. So if you have less than 128 bits, so the remaining bits will be added like as 0. So it will be filled with 0 to make it 128 bits. Now the locators, these bits has two parts. So one is basically the block, the segment routing block, and the other part is called the node. So you can identify where to go or who is the my target destination to go inside the locator. And so this part usually is like a global block. Remember I told you that global block is known to the other segment routers in the domain. And the function and the argument, this can be local. So once you reach the destination, it knows what to do with that packet, okay? So in general, this can be, but there can be very specific cases, but because I don't have time, I'm not going to go very deep into like different cases. But this is like a generic concept of how this seed is formed. So you might see a seed instead of MPLS level, you might see like this, and this might mean something to that node, and it will basically do the same thing as it does for MPLS data plane. Okay. So the function, the behavior, and the arguments. So function, I said like these values are the function. And what is the endpoint behavior? Once it comes to the endpoint, what type of actions it's going to take is the behavior. And the argument can be different types of options as well, associated with the function, this one. So this is basically an opaque, like an instruction. And why it's opaque, because you will see why it's opaque, but it's like the local behavior that's related to the endpoint, and the seed will define what type of actions it's gonna take. And there are two types of seeds. One is called routable, the other one is non-routable. Remember I said global seed means you want to tell people about this. And the non-routable is the local one. You don't need to tell everybody. It's the endpoint who needs to know about it. That's it. So there can be many different behaviors, and each behavior, you see some function is there, you see. So in short, because the list can be very long, and I don't need to go like with every single one, but in short, if you see end, it means an endpoint. And then if you see some kind of optional indicators there, it means it's some task or some function. So the endpoint, and this is the cross connect, for example. The endpoint, this is the table. So let's say if you want to instruct the endpoint to do a routing table lookup, so you basically telling n.t, something like this. If you want to check the cross connect at the endpoint, for example, a VPN cross connect or VRF cross connect, for example, L2 or L3 cross connects. So you can use this. So this can even be extended to V4 and V6. So this part, you see all of them related to 6 or 4. These are actually table. That means you were telling them that the endpoint that don't just look at my segments, but once you finish with segments, remove the header and look at the payload. There are more headers, and finally match it with your routing table and then decide which interface to go. So it's like decapsulation and then routing lookup. Remember, we are talking about this PHP. So the level will be removed, and then finally, if you want to send it to CE, I have to send it as a normal packet, not really a MPLS packet, because the other side does not understand MPLS. So the same thing. So this is D is the decapsulation, and then you can have either cross connect or table and things like that. So it's like the name and related function. Each function has some meaning to the endpoint. Flavors. The function needs a flavor to mention, otherwise the router will not behave as you are expecting. So there are 3 different flavors. In MPLS, we had one flavor only. We had the PHP or penultimate hop popping. But here we have, actually in MPLS, we also had ultimate hop popping, but we don't say that. It's like not needed to say. But here there are 3 different flavors, and we need to know each of their definitions so you understand how it works. First one is already we know, PHP or penultimate hop popping. Here it's called PSP, penultimate segment pop or popping. And the next one is ultimate segment pop. So penultimate segment pop or PSP is I want the second last node to remove the top segment. And this one is I want the last node to remove that, not the previous node. And the next one is I want the last node not just to remove the segments or segment routing header, but also check the destination information in the payload and then look at the routing table and then take a decision. So this is like decapsulation. And the decapsulation means you also want the routing table lookup as well. So this is like USD. It's not US dollars. Yeah, so the choice of the flavors is decided by the source. So in segment routing, you'll see everything is decided by the source. And that's similar to source routing, but actually not source routing. So what is PHP? I already explained. So how it works is the last router of the whole segment, the last router will not do the hopping. It's the previous router or the penultimate router will do that. And for this case, this is an example. It's similar to MPLS that we had. So we had this diagram before, right? Before the break, we had similar thing. So this one. So R1 has an instruction. Here is the instruction, and instructions are basically policies, and then each of the instructions are called segments. So I have now two segments. One is R1 to R3. I have to go till R3, and the second segment is R3 to R5. So the first segment is the active segment at the moment. So the destination is R3, not R5. So the packet goes, normally normally the IPv6 packet transfer happens based on normal routing table by R2. It comes to R3. R3 looks at the header. It finds that I'm the last destination. But if I look at the list, I have one more task remaining. So I'm not the ultimate destination. So I have to now copy the next one here, make the new packet as a segment endpoint. I would like to make the next packet. In our previous example, this header remained. This one became here like a IPv6 header, but you see penultimate hop popped the segment routing header because it's the last router in the segment. Now by last router, this should be the last router, but by last router I mean who is dealing with the header is the last router. You see, this one does not deal with the header. Header means not segment routing header. It deals with the IPv6 header, not the for this router. This packet is just an IPv6 packet, not a segment routing packet. For this router, it's a segment routing one. For this router again, it's just a normal IPv6 packet. So header is here or not does not make any difference to R4. So the last router means in the list. What is the last router in the list? So this one is R5. The previous router is actually R3 in the list. So that is the penultimate segment popping. Okay. So this is useful in some cases to speed up, because this router does not even need to know whether because this is actually no meaning to R5, because it's not going to even look at it, because this is the last router and segment left will be 0. Basically, the only job it will do is remove it. Why it needs to do that? It can be done by this guy, because this guy already processing it. So it's not a new process for him, but for him, it's going to be an additional process. Why we do that? So just simply remove it. Now, sometimes this can be problematic when I have to identify which VRF I have to send. Then if somebody removes the header, how can I find out which VRF I'm going to talk about, right? You understood, right? Or if I am the destination, I have to process something. Then I also need to know the headers, because I have to first decide, okay, I am the destination, so let me decide what I'm going to do. So this is okay when it's simple IP connectivity with a neighbor. This is okay. But this is not okay when it's a VRF, or I have to find out which service I want to serve. It's a VPN, and very difficult if somebody remove it. So this is not suitable for all the different tasks. And this time we are not talking about MPLS level that you remove one level, but the next level still exists. It's not that MPLS level stack. The stack happens in the header itself, not like there are more headers. I'm just removing one header, not like that. The list is not an independent header. The list is just part of a header. So if I remove the whole header, very difficult for the endpoint to find out which VRF it belongs to. So in that case, PHP may not be a good choice. And in the lab, we'll see that it does not work if I remove the hop in the penultimate router. Now the other options is ultimate segment popping. It's important because like I said, VRF detection, you might need the USP. So in that case, the penultimate will not remove it. It will come to the last router of the segment, a very ultimate last router. It will remove the header. And of course, by that time, it will understand which VRF it should pass to. So that's called ultimate segment pop. And this is the decapsulation if it needs to look at the routing table as well, not just the VRF. In VRF, you don't look at the routing table. If you know who is the VRF, you just pass the packet to the VRF. But if you want to look at, because if you might have multiple customers in one VRF, if you want to look where to go, you can do that. But originally, actually, you don't want that. You want one customer in one VRF, usually like that. But that's what the cross connect concept came, right? It can have multiple. It's like a LAN. It can have multiple customers or multiple CE in one VRF. So because telco infrastructure is quite different than the normal, internet infrastructure, normal like the enterprise infrastructure. Telco can have so many different requests because customers of the backbone operators are banks, academic like universities, the enterprises, and the data centers. So they might have different types of. So it's not just one different one. Okay, now to carry the information. Remember, I said LDP is a problem for MPLS because it's an additional, not a problem, but it's an additional process. RSVP TE is a real problem. It's